So, good morning everyone. This is my next lecture following with the first lecture, which is based on optical fiber link and ray transmission theory. So, this is lecture number 2 and we have cylindrical modes in this lecture, fiber types and its parameters. So, what is cylindrical modes? So, if we see cylindrical modes, the cylindrical waveguide, however, it is bounded in 2 dimensions rather than 1. Here we consider 2 integers, that is L and M, as compared to the planar modes, which are necessary in order to specify the modes here. So, for the cylindrical waveguide, we therefore refer to TE-LM and TM-LM modes. So, if you remember, so in planar modes we have TE or TM modes. In cylindrical, this is for planar modes. So, in cylindrical, we have TEM or you can say TE-LM for electric fields, and similarly TM-LM for magnetic fields. So, this is L and M are basically integer numbers, and we specify here how the L and M will vary. So, these modes correspond to meridional rays travelling within the fiber. However, hybrid modes where EZ and SZ are non-zero also occurs within the cylindrical waveguides. So, these modes which results from skew ray propagation are designated as HE-LM, that is hybrid electric LM or electric hybrid LM, depending upon whether the component of H or E is larger contribution to the transverse field. If the H contribution is larger, then it is called HE-LM. If E contribution is larger, then it is called EH-LM. So, analysis simplified by considering fibers for communication purpose. Here we satisfy the weakly guided approximation, that is delta is very much less than 1 for a small grazing angles theta. So, for weakly guiding structures with dominant forward propagation, mode theory gives dominant transverse field components. So, here we have full sets between HE, EH, TE and TM modes. So, there are 4 modes here as compared to TE or TM modes in the case of the planar waveguides. So, these linearly polarized modes are not exact modes of the fiber, except for the fundamental lowest order mode, which is called as LP01. So, lowest order mode, that is fundamental mode, which is called as LP01 mode, and weakly guiding fiber relative refractive index difference here is very small, as then HE and EH mode pairs occurs which have almost identical propagation constant. Such modes are called degenerate modes or having the same propagation constant. So, the superposition of these degenerate modes characterized by a common propagation constants corresponding to a particular LP modes regardless of their what HE, EH or TE or TM field configuration. So, here with this linear combination of the degenerate modes obtained from the exact solution provides a useful simplification in the analysis of the weakly guiding fibers. The relationship between the traditional HE, EH, TE and TM modes designated and the LP, LM modes designation is shown in the table here. In the next slide, we will discuss the table how the HE, EH, TE and TM modes are to be designed. So, the mode subscripts L and M are related to the electric field intensity profile for a particular LP mode. So, correspondence between the lower order in linearly polarized modes and the traditional exact modes from which they are formed is represented here in the table. So, in the left side we have linearly polarized mode, that is LP01, LP11, LP21, LP02, 3112 and LM. The exact modes are given in the right side, that is LP01 has only the H contribution majorly, that it is called as HE11. Similarly, LP11 we have HE21, TE01, TM01. So, instead of only 2 modes, we have here 4 modes combinations. Either it can be a TE, TM or HE, or it can be purely HE, or it can be HE or EH modes. So, we have these combination according to the linearly polarized modes. So, now we will discuss the intensity profile of these modes. So, electric field configurations for the 3 lowest LP modes in terms of their constituent exact modes, that is LP mode designations, exact mode designation, electric field distribution of the exact modes, intensity distribution of EX for exact modes, indicating the electric field intensity profile for the corresponding LP modes. So, it may be observed from the field configuration that maybe electric field is in the X direction, that is the transverse direction, or is in the Y direction. Both are identical for the modes which belongs to the LP modes. So here in the figure we have shown the first diagram is for x direction and the next second diagram is for y direction. Both are similar to each other, but the direction of the propagation of the electric field is different. Similarly, we have in the diagram that is LP01, HE11 which has the unidirectional electric field. Similarly, LP11 which has two intensity profiles. It has horizontal intensity profile and one is vertical intensity profile. Similarly, TM01, HE21, then EH11 which has LP2 which corresponds to the linearly polarized mode LP21. So, it has 4 intensity profiles. Similarly, for HE31, it has 4 intensity profiles. So, these patterns are called flower patterns, the last one that is LP21. So, the variation of the Bessel's function for L is equivalent to 0, 1, 2, 3. You can have the Bessel's function at J equivalent to 0 is much higher as compared to J0, J1, J2, J3. It will be reduced instantly. Similarly, the modified Bessel's function you can see from the graph, that is K1R and K0R against the L equivalent to 0 and 1. So, we have the solutions for Bessel's function. We will also discuss these Bessel's function in the next lectures. So, you can have the two parameters from the Bessel's function, that is U and W. So, with this U and W, we can have our equation for the normalized frequency, which is V. V is equivalent to U square plus W square, which is around Ka N1 square minus N2 square. This is N1 square minus N2 square. So, this is Ka under root N1 square minus N2 square. So, with this we can easily calculate the value of the V. So, what is V number? V number is basically normalized frequency which is expressed in terms of numerical aperture. So, V number can be described as 2 pi by lambda A into under root N1 square minus N2 square, or it can be also represented as V is equivalent to 2 pi by lambda into A into Na, which is Na here is numerical aperture. So, normalized frequency is a dimensionless parameter and simply it is called as V number or value of the fiber. It combines in a very useful manner the information about 3 parameters. So, if you increase the diameter of the fiber or the radius of the fiber, V number will increase. If you decrease the wavelength of the fiber, the V number will automatically increase. Or if you increase the delta, that is relative refractive index difference or numerical aperture, in that case also V number increases. So, how the V number will be used for having the calculation of the number of modes, we will see in the next slides. So, what are the allowed LP modes? What are the allowed linearly polarized modes? So, we have already seen the combination of the exact modes and the linearly polarized modes. So, we can have an analysis of what are the Bessel's functions. So, we discuss the Bessel's functions and the modified Bessel's functions. So, the allowed modes are here, which is represented as LP01, LP1102, as same as in the table we have discussed LP12, LP03, and similarly we have HE1, which are exact modes. So, upper side is the linearly polarized mode and the lower side is the exact mode. So, this is linearly polarized and this is exact modes. Now, we have a cutoff value of the V number, that is for different modes. So, for LP01 it is 0, for LP11, so beyond LP01 next mode is LP11. So, the cutoff value for LP11 is 2.405. So, for calculation purpose we take the value of the LP11. If we have to calculate suppose we have to calculate the diameter of the fiber or the wavelength of the fiber for a particular cutoff normalized frequency for LP11, we usually put 2.405. Similarly, for LP02, it is 3.83. So, you have to remember these values for the calculation purpose in numerical problems. So, what are leaky and guided modes? So, limit of the mode propagation, as we see that the propagation constant inside the core is Kn1 and the propagation constant outside the core is, or in the cladding, is Kn2. So, the propagation constant must be Kn2 greater than Kn2 and less than Kn1. So, when beta equivalent to Kn2, the mode phase velocity is equal to the velocity of light in the cladding and is no longer properly guided. So, mode is said to be of cutoff mode in this case. So, whenever the propagation constant is similar to Kn2, the mode is said to be cutoff, or you can say it is unguided mode. So similarly, when beta is less than Kn2, it is also unguided modes. When beta is greater than Kn2 and less than Kn1, in that case only the modes will be properly guided inside the fiber. So now we have mode coupling. So mode coupling is basically the coupling of the modes inside the fiber. So there are several perturbations in the waveguide. These perturbations can occur due to deviation of fiber axis from the straightness. It can be variation in the core diameter due to these perturbations occur, or maybe there are some irregularities at the core cladding interface or refractive index variation. So from the figure itself you can see that initially we have TIR principle when there is no irregularities in the core cladding interface. But here I have drawn a irregularity at the core cladding interface, and now the light is hit at the core cladding interface, and it will be not having a total internal reflection, but it is having radiated away from the core cladding interface. So due to these irregularities, maybe there will be a change in the direction of the light, and the light will be not easily guided inside the fiber. So these are some conditions in which the perturbations will occur, and these conditions will make the mode coupling or the mode mixing not proper. So we have to see whether there is no irregularities at the core cladding interface or no refractive index much variation at the time of the fabrication. So now we have types of fiber. The first fiber is step index, grade index fiber categories. So you can see from the word itself, that is, it is step index. So we have two type of fiber in step index. First one is a single mode fiber and the second one is a multi mode. The single mode fiber has a typical diameter around 8 to 12 micrometer. As compared to multi mode fiber, it is having 50 to 200 micrometer inside the core. So you can have a single light inside the fiber in single mode fiber, but there are multiple modes inside traveling inside the fiber in the case of the multi mode fiber. The index profile are similar to each other, both having the step index profile. There is refractive index constant, that is N1 inside the core and N2 outside the core or in the cladding. In the third case, we have a diagram based on multi-mode graded index fiber. So in multi-mode graded index fiber, we have a parabolic refractive index profile, that is at the center of the core, the refractive index is much higher, but as you go beyond the center of the core towards the core cladding interface, the refractive index reduces. So there is some profile parameter conditions inside the fiber in the case of the multi-mode graded index fiber. We can see from the expression itself. So the core diameter the same as the multi-mode step index fiber in the case of the multi-mode graded index fiber. So we can see from the step index profile, we have NR is equivalent to N1 for R less than A, and R greater than equivalent to A, it is N2. So this is the diagram showing the multi-mode step index fiber. The first diagram, the second diagram is the multi-mode single mode step index fiber. Both having the same step index profile, but the number of rays inside the fibers are different. In single mode, it is only one mode. In multi-mode, there are multiple modes traveling inside the fiber. So this multi-mode fiber have different attenuation, different type of attenuation. We will see in the next later slides or the later lectures that it has much more dispersion as compared to the single mode fibers. So how to calculate the modes, number of modes in single mode fiber? We can easily calculate with the help of the V number. So V number is the normalized frequency. So we have number of modes, that is V square by 2 in the case of the step index multi-mode fibers, or step index graded index fibers, or for multi-mode graded index fibers we have different formulas. So here we have an example, a multi-mode step index fibers of core diameter 80 micrometer, refractive index 1.48, refractive index difference 1.5% and operating wavelength is 850 nanometer. So here simple we use formula 2 pi by lambda into A into N1 into NA, or you can say A into NA, or 2 pi by lambda into A under root. These two formula you can use, whether whatever the formula you are using, it's convenient to you. So a multi-mode step index fiber diameter is given, 2A is given, that is 80 micrometer, then core index given is N1 is given 1.48, A into N1 into NA. This is A into N1 into NA. Okay. So we can have a number of modes we can calculate, that is around 2873. With the previous slide, you can see the formula, that is how to calculate the V number. So V number can be calculated with V is equivalent to 2 pi by lambda into A under root N1 square minus N2 square, or 2 pi by lambda into A into Na. So for gradient index fiber, we have index variation, that is Nr is equivalent to N1 1 minus 2 delta R by A to the power alpha to the power 1 by 2 for R greater than equivalent to 0 and less than equivalent to A, and Nr is equivalent to N2, or you can have N1 1 minus 2 delta to the power 1 by 2 for R greater than equivalent to A. So it has a parabolic refractive index profile. So the core index is maximum at the center, and then it will be gradually decreasing due to this parameter, which is profile parameter. So here alpha is profile parameter. So you can see from the figure itself that it has a refractive index which is maximum here, but it is reduced slightly from the core axis towards the core cladding interface. We have three different profile parameters here in the next diagram, that is alpha equivalent to 1, 2 and 10 and infinity. For alpha equivalent to 1, it is called triangular profile. For alpha equivalent to 2, it is parabolic, and for alpha equivalent to infinity, it is same as step index profile. So you can have formula ms is equivalent to alpha upon alpha plus 2 v square by 2. You put down here alpha equivalent to infinity, we have v square by 2, alpha equivalent to 1, we have v square by 6, and for alpha equivalent to 2, it has v square by 4. So these three formulas you can use for different kind of fiber configurations. So how the gradient index fibers are having that local numerical aperture, it has axial numerical aperture and the modes. So modes we have alpha upon alpha plus 2 v square by 2. So these are some design parameters: numerical aperture, relative refractive index difference, and these are some ideal values for the single mode fibers. Normalized frequency, which we have discussed already, that is around 2.405. Delta is around 1% for multi-mode fibers and less than 0.4% for single mode fiber. Numerical aperture lies in the range 0.12 to 0.20 for single mode fiber and 0.15 to 0.25 for multi-mode fibers. And lambda c is the cutoff wavelength. You can calculate with the formula, that is 2 pi by lambda into A into N1 under root 2 delta. With that formula, you can easily calculate the value of the lambda c. So we have V is equivalent to 2 pi by lambda into A into N1 under root 2 delta. With this, lambda c can be calculated, that is 2 pi by Vc A into N1 under root 2 delta. So thank you so much. So in the next lecture, we will discuss about the sources, optical sources. What are optical sources? LEDs and lasers. And later on we discuss detectors, and then when at the last we discuss about the budgeting, how the link will be used for the combinations of the lasers and the LEDs and the detectors. Thank you.